In this video, we're going to look at section 8.4 on alternating series. So to get started, we're going to begin with example 1, where we look at a situation involving an alternating series. We're going to define an alternating series here in a little bit, but this example will help us get an idea of what types of behavior these series have. All right, so example 1 says, discuss the convergence of the alternating series given by the sum of n equals 1 to infinity of -1 to the n minus 1 over n. Okay, so to get a sense of what's going on here, let's go ahead and compute some terms of this series. So let's go ahead and start with when n equals 1. What do we get? So when n equals 1, we have -1 to the 1 minus 1 over 1. So it becomes -1 to the 0 over 1. Any number to the 0 power is just 1. So we get 1 over 1, which is 1. Okay, let's do this again. So let's look at when n equals 2. So when n equals 2, we have -1 to the 2 minus 1 over 2. So it's -1 to the first power over 2, which is -1/2. All right, let's just do this a couple more times so we can start to get a sense of this series. So when n equals 3, we have -1 to the 3 minus 1 over 3. That becomes -1 squared over 3. Notice what happens there. -1 squared becomes +1, so we get +1 over 3. All right, let's just do this for one more n. So when n equals 4, we have -1 to the 4 minus 1 over 4, which is equal to -1 to the third power over 4. But -1 to the third power means that we're multiplying -1 by itself 3 times. So 2 of those negatives cancel out, but we have 1 negative remaining, so we get -1/4. Okay, so we can write out this series then. This is just the sum of 1 minus 1/2 plus 1/3 minus 1/4. If we notice, the pattern will continue, we'll add and then subtract just unit fractions here. Okay, cool. So then we're given a little visual here to help us kind of understand the question about whether or not this series converges. So let's see how we can interpret this illustration. All right, so what we can do is interpret this first value here as just being at 0. And so first what we're going to do is add 1 to 0. So that's our first term. So if we added 1, we're over here at 1. Okay, so we just look at the first term in our series 1. Recall that's just a partial sum using one term. So that's equal to 1, so that would be S sub 1. So recall S sub n is just the sum of k equals 1 to n of a sub k. So it's just the sum of the first n terms. So the sum of the first 1 term is just S sub 1. But now in our next term in our series, we're going to subtract 1/2. So if we're starting at 1 now, say I've added 1, now I'm going to subtract 1/2. So I'm going to go in the negative direction 1/2. So now I'd be here at S2, which in this case would be at 1/2. Because 1 minus 1/2 is 1/2. All right, but we could keep doing this. So now from that 1/2, I'm going to add 1/3. So now I'm going to look at the partial sum of 3 terms. So I add 1/3. It'd be somewhere here. That would be S sub 3, my third partial sum. And I can keep doing this. Now I'm going to subtract 1/4. So S sub 4. So I'm going to go back a little bit. I'm not going to quite cancel out that 1/3 that I added, but I'll be somewhere here. So it'll be S of 4, so S sub 4. And then what would be next? Well, next I would add 1/5. So we'd have S sub 5. So notice what's happening here in these partial sums. So we start out at S1 here, S2 here, S3, S4, S5. what do we think might happen as we continue looking at our partial sums? Well, we see that we're bouncing back and forth in our partial sums, back and forth about some amount. Maybe here. So it's looking like we're going to converge to some value that I'll call S. And this is just observing the behavior of our series and these partial sums. So let's write down that observation though. So it appears that our series should converge to a number S. And again, notice why we might think that. Well, these partial sums go back and forth. They never cross each other, but they kind of narrow in on some number. So we think that it's probably going to converge. So what are some properties of our series that make this behavior happen? So I'm going to write properties that make this behavior. So I encourage you to pause the video and think for yourself, what are some properties of our terms that are providing us with this behavior that we're seeing? But let's discuss together now. So first of all, notice that these terms alternate positive and negative. So in particular, for our series, this -1 to the n-1 power means that n-1 is going to go back and forth between being odd and even. As we add one more n, then it's going to rotate, then that number will rotate from being odd to even to odd, etc. So then -1 to that odd or even power is going to rotate from positive to negative. And we see that in our series. +1, -1/2, +1/3, -1/4. So we're going to make that observation. So we are alternating signs. And in this case, we started with plus, and then we went minus, plus, minus, etc. But we could have also started with negative and then added. So in that case, we would have just started going in the negative direction first, and then positive direction, etc., back and forth. So that is what we mean by alternating. That's why we called this series alternating, and that's what we're going to see in the definition. Okay, but what are some other properties of this series that we're seeing? We'll notice that the terms in our series, just 1, 1/2, 1/3, 1/5, 1/4, 1/5, so those absolute values of the terms, they go to 0. They get smaller and smaller. And we see that in the sizes of these arrows. So 1, 1/2, 1/3, 1/4, 1/5, 1/6. So the sizes of the arrows get smaller. So how would we express that? Well, that means the limit of the term 1/n, meaning if we get rid of that negative sign, that limit goes to 0. And so that's part of what's giving us this apparent convergence here. These terms get smaller and smaller, so our arrows would move back and forth less and less. We wouldn't go way over to some other spot or go zero in on some fixed distance back and forth. Okay, enough of that. Cool. Okay, then what's a final observation we can make? Well, one thing is if we just look at the terms, 1, 1/2, 1/3, 1/4, 1/5, so those absolute values of the terms, notice that we're getting smaller each time. So not only are they going to 0, but they're in fact always less than the previous term. So 1/n is going to be bigger than 1/n plus 1. And that's what's allowing these arrows to kind of fit in with each other, meaning that the next term we subtract, we're not going to subtract more than that previous term that we added. So each time we're not going to be able to overpass the previous arrow of sorts. Okay. So these are three properties that are going to be important when we are considering an alternating series. And we're going to see that here in our first theorem of this section. So let's go ahead and look at that theorem now. So this is called the alternating series test. So in this situation, let Bn be bigger than 0 for all n. A series of the form, the sum of -1 to n minus 1 Bn, or the sum of -1 to the n Bn, is called alternating. It's called an alternating series. So notice that the Bn's are all positive, but this coefficient on the Bn's, this -1 term, either raised to the n or n minus 1, will alternate between -1 and +1. So the actual terms of the series that we meet will rotate from positive to negative. But if we consider those terms without the negative sign or positive sign, then those Bn terms, or Bn is what we're calling that term. And those will always be positive. Okay. Okay, so that's cool. So what about such a series? Well, if that series has the following two properties, and that is, number one, if the terms, the Bn, go to 0 as n goes to infinity, and if the nth plus 1 term in the sequence, or in the sequence making up the sum, is less than or equal to the nth term for all n, then the series converges. So we saw this behavior in our series of example 1. So recall our series looked like the sum from n equals 1 to infinity of -1 to the n minus 1 over n. And that is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus plus, etc. So in our situation, our Bn term would look like 1 over n. So we can read that in our series. Maybe I'll just highlight it here. So for us, Bn is equal to 1 over n, and we can check that we have these two properties, a and b, satisfied. So for a, the limit as n goes to infinity of Bn is just 1 over n, and yes, that indeed goes to 0. And for part b, we need to check that the nth plus 1 term, so 1 over n plus 1, is less than or equal to 1 over n. And yes, that indeed always happens when our denominator is larger here in a fraction. That whole fraction is going to be smaller. So our series would converge, as we suspected. All right, and notice that when we had our properties of our series, we required that these terms alternate from positive to negative. Not required, but that's what we observed. And that's what we're seeing here in the definition of an alternating series. So we didn't need to check that property because we saw that we had an alternating series. Okay, but what's really neat about alternating series is that we also have an idea about how close we can get to finding that sum, the convergent value of our series. And that's stated here in our next theorem. So that theorem is the alternating series estimation. So it says if S is the sum of an alternating series, so that number that the series converges to, that satisfies the condition A and B in the above theorem, meaning our series converges to some S, then the difference between S and the partial sum of n terms can be calculated, not specifically, but we can bound it. And it's going to be bounded by the nth plus 1 term in our series. So I'll explain what that means a little bit in the context of our example 1. So then what that means is if we say, look at the first 5 terms in our series, 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. And let's say we just stop there. We add up these numbers. So that's going to be our S sub 5. So what this theorem tells us is that if we consider the error or the distance between our partial sum, S sub 5, and the value our series converges to, this error is going to be less than or equal to that 6th term in our series. It will be less than or equal to 1/6. So we can get as close as 1/6 to our convergent value by adding up the first 5 terms of our series. And so that's what the rest of this says. Sn is the sum of the first n terms of the series. And we can see that should kind of make sense when we look at these arrows here. So if we stop at, say, adding up S sub 1, S sub 2, and then look at that distance away from actually what S is, this distance, so this error that we've made, is going to be smaller than that next term in our series. And we can see that, okay, if we add up the first 3 terms, so we're here, and look at this distance now between S and S3, this distance is going to be smaller than the next term in the series. Do we see that? So here's my error. Here's the next term in the series. And that error is smaller than that next term. Cool. All right, so then we can just finish up this note here. It says note. So what this says that if we use the first n terms to approximate the sum of the series, so using the first n terms would mean computing S sub n, then the maximum error in the approximation is b sub n plus 1. So we can get within b sub n plus 1 by adding up the first S sub n terms. Awesome. All right, great work going through this video. Feel free to rewatch any parts of this example or of this explanation of the theorem to help familiarize yourself with these new tests.